The example would be a hockey player accelerating off the line in defensive short corner in order to stop the drag flick. Acceleration is a vector quantity. This is the rate at which an object changes its velocity and is measured in meters, and this is measured in meters per second squared. Finally, impulse and momentum are another factor in linear motion because they can affect the motion of an object. Momentum is when an object can be moved, is when an object is moving and is going to be hard to stop because as it gradually builds up pace and force, the weight of the object will increase. Impulse, however, is an impelling force or motion which causes sudden change in the motion of an object. An example of an impulse force is thrust. Examples of this would then be how fast a player can get to their top speed when transitioning from attack to defense during a game. There is also curvilinear motion, which is where an object travels along a curved path. A general sporting example of curvilinear motion would be making a J-run in hockey. A J-run in hockey is where you start off by running in a straight line, and then towards the end of your lead you make a curved run to either your left or your right in order to create space. However, a more specific basketball example could be when you post up into space looking to receive the ball, but then curve back out to make space for someone else to make another lead. Finally, there is angular motion. Angular motion is the motion of a body part around a fixed point or an axis. A general example of this would be when someone is bowling the ball in cricket and their arm is rotating around the joint in their shoulder, causing angular motion. However, an example in basketball would be when an attacker is performing a block. This is where their arm will be raised above their head, and if they are swinging forwards to block the ball, there will be a slight rotation around the shoulder joint. However, there are not many examples in basketball of a full rotation, so this is as much of an angular rotation as I could find. Next, we'll be moving on to the two tests that we completed. The two tests we did were the vertical jump test and the 20-meter sprint test. This is because they are both relevant to basketball. The ideal methods of both the jump test and the 20-meter sprint is that they are the most accurate and precise way to perform the tests. However, both these tests have their negatives, particularly in terms of their accessibility. Firstly, the vertical jump test is best performed when you use force plates. Force plates work by measuring the ground reaction force of the performer. But before the performer performs their jumps, you must calibrate the equipment by turning it on, setting it to 0, and then checking the plates are level prior to weighing the participant. And then once you have weighed the participant, you must reset the scale back to 0 again. The force plates are able to take up to 1,000 readings per second of the force being produced by the participant. This will equate to the total vertical jump score. Whilst doing this, the force plates can measure the amount of force that is produced by the participant at each stage of their jump. This will also enable the researcher to see where the weaknesses and strengths of each individual participants are. This means that it can be extremely useful for elite athletes, in particular to help them find improvements and areas to improve using jump plates. However, the accessibility for force plates, the general population is very poor. This is because they are so costly, and that in order to use them, you'll more than likely have to pay for a session in a lab at either a university or a research centre, which is also expensive. The force plates will also require a lot of knowledge and experience in order for you to be able to use them safely and effectively, and in order to get the most accurate result possible. And then for the 20-meter sprint, the ideal test method would be to use light gate and high-speed cameras. You could get a digital sensor that has only two settings on, which are on and off. This means that when the sensor detects something going through it, the light beam would break, and as soon as this beam is broken, then it will start to record the time until they get to the next gate at the end, or wherever it has been placed along the distance. The ideal way to set up for a 20-meter sprint would be to have a light gate at every 5 meters, so that we were able to get the whole 20 meters plus split times for every 5 meters. To make this method even more effective, we can use cameras. The most effective cameras would be 2D and 3D Vicon cameras. These cameras are used to analyze the movement of participants in a much higher level of detail. The Vicon cameras have little motion tabs that will be placed on the joints of the participants and will allow for extra analysis of their movement. The software used to help analyze the movement would either be Quintet software or Dartfish. The reason you could use the highest level of detail would be by using high-speed cameras. This is because they can take up to 1,000 frames per second, meaning you will be able to catch every minor detail of movement. You will also be able to adjust the shutter speed for when you take photos. If the shutter speed is faster you can change the shutter speed to be faster or slower depending on the speed it is set to do. The whole physics of the camera setup is crucial to be able to get all the angles. This process is called triangulation. To do this properly, all the cameras must be set up perfectly, including making sure there is no tilt. You can make sure there is no tilt by using a spirit level and providing you can make sure it is not tilted by using a spirit level. You would also have to make sure that it is on a tripod in order to make sure you can catch all the motion, as you may need to pan the camera whilst the participant is performing motions to get it all perfect. As it may be necessary for you to have a few practice runs though to make sure you get everything down. On a negative side of things, there is a chance of perspective error because the camera setup might miss something due to them being set up in a certain way. An example of this would be the measurements of an angle may be different due to where the cameras are set up. Similarly to the force plates, this setup is extremely expensive and only labs and research centres tend to have access to this equipment or level of setup. On top of this, there is a huge amount of knowledge that is required in order for you to be able to carry out these tests in order to maximise the potential due to the limitations. However, there were limitations when we came to do the tests, so we had to come up with different methods to do them. The preferred methods we chose to do whilst maintaining as much accuracy as possible in the circumstances where we chose to do a 20-meter sprint test and a tachymat jump test. To start with the 20-meter sprint test, we firstly set up 5 cones on the court, one at the start point, and then one for every 5 meters until the finishing 20 meters. We did it this way so that we would be able to time each participant as they went through each 5 meters. In order to time the participant, the timer stood at the halfway point and then said, "On your marks, get set, go." And when they said go, the participant was allowed to move. The timer started the stopwatch as soon as they said go, and then press lapped every time the participant passed one of the 5-meter cones in order to be able to get their split times. They then stopped the timer as soon as they saw the participant cross the full 20-meter time. The main problems with this test is that the fact there is a lot of room for human error, meaning that the test would most likely not be 100% accurate, as the timer may not have started it as they started moving and may not have stopped it as they stopped moving. However, it was as accurate as we could have possibly made it due to the circumstances. Each participant did 3 20-meter sprints to make sure that we maintained the best level of accuracy and validity. In terms of the vertical jump test, again due to limitations, we were not able to use force plates, so instead we used the tachymat, which is still accurate in relation to the height of the participant. We also weighed the participants in order to be able to work out their force. To do this test, the participant has to strap a belt around their waist and then tighten the cord to make sure it is completely straight from the floor to their hips. Then the participant must jump as high as they can and then read the score that is shown on the belt. We made sure each participant done this 3 times, again in order to make sure that the tests were reliable and valid. However, even though this test is still quite accurate, there may be room for error, as participants may forget to completely tighten the rope when it came to their second or third attempts. Next, we'll be looking at the results of these tests. The first results are for our sprints. You can see for the results of our sprints, there are 3 different graphs that we are able to get from our results. These are distance, velocity, and acceleration. As you can see here, there are 2 sets of results. The top set is my player, and the bottom set is the model player. As we can see from our my player's data, they completed their sprint in 3.21 seconds, which is an okay time. However, as you can see, from 0 to 5 meters, it took them quite a long time to start accelerating compared to the model player, who accelerated pretty much straight away, as the my player only completed the first meters in a time of 1.82 seconds, whereas the model player completed it in under 1 second. Next, from 5 meters to 10 meters, the participant accelerated rather rapidly compared to the model player, as there was a much steeper increase in the line. However, the model player, as you can see, has a more consistent acceleration, therefore showing that they can continue accelerating for a maintained period of time. Next, from 10 to 15 meters, you can see that my player is still accelerating. However, there is a slight drop in the steepness of the line, therefore showing that they have slowed down a tiny bit. However, once again, the model player has still got a constant acceleration through the 10 to 15 meter point. And then finally, for the last 5 meters, my player then speeds up again for the last 5 meters, whereas the model player again continues at the same speed. From these results, we can suggest that the model player is better because they have a constant acceleration throughout, as should be expected for someone completing a 20-meter sprint, as you should be able to accelerate the entire way through the sprint. Whereas my player took a while to accelerate, and then slow down, and then it started accelerating again. This would be bad for a game situation